Welcome to our video on average rate of change of a function. Here are our two objectives. We'll see that basically we're just looking at average rate of change and then the fact that linear functions have a constant rate of change. So functions are often used to model things in the real world, and things in the real world don't tend to stay static, so they're usually changing, and thus functions often model changing quantities. And usually it's over time. So a lot of times you'll see the x-axis is really represented as time, and you'll get a function in terms of t instead of x. So let's look at some of these examples of average rate of change where we want to see how much these functions are changing over a certain period of time usually, but you can just think of it as a distance along the x-axis. So we all understand speed and how it works. We all know that if we drive 120 miles in 2 hours, then our average speed was 120 divided by 2 equals 60 miles per hour. And we all know that during that 2-hour time, we didn't do 60 the whole time, right? Sometimes it was above 60, sometimes it was below 60, but we averaged 60, right? Well, that's what we're talking about when we're doing an average rate of change over a function. It might increase faster and slower over a certain interval, but over a certain distance, and usually we'll talk about it as a certain time, we'll have a set increase, and that increase divided by that time gives us an average. And so that's the average rate of change for that function. Here's a typical example. This could be, your speed function. And like we said, you're not going to have a constant speed. You're going to speed up and slow down. So you're going to have this curved function. But then we have over a 3-hour span, you covered a total of 150 miles. So that means on average you did 50 miles per hour, right? And all we're doing basically is calculating the slope of the straight line in between those 2 points. If you were able to, oh boy, that's a fantastic straight line. Let's try that again. If you were able to make a linear function, right, a straight line between those 2 points, the slope of that straight line would be change in y over change in x, right? And its change in y is its change in height, which it went from 50 to 200. So 200 minus 50 gives you 150. And then the change in x, it went from 1 to 4. So 4 minus 1 is 3. Change in y over change in x, 150 over 350. The slope of that line is 50. So you can see the average rate of change is just slope of the straight line between 2 points on a function, which is why we're later going to talk about how the average rate of change of linear functions is constant because it's already a straight line. Okay, so here's where we're talking about how this all worked. You can see I wrote down basically what we just discussed on the previous slide. And then here's some math to also talk about what we did, right? Again, change in y over change in x. Now, you'll note that the average speed on this function is not going to be constant. For instance, if we go from 3 to 2, or from 2 to 3, we get 140 minus 75, and that was only a 1-hour span, right? So we divide that by 1, and we get 65 miles per hour. So if we look back over here, going from 2 to 3, so here's my height at 2, which looks like it's about 75. Here's my height at 3, which looks like about, 125, but it's a little bit less, right? So the numbers that we used are 140 and 75. Right, so here's 150, so it's somewhere in between there. I would have gone with 125. The author thinks 140, but you get the idea. In either case, we're going to get a different rate between these 2 points because the slope of the line between those 2 points is not going to be the same as the slope of the line between those 2 points. They look pretty similar, and they are, because 50 and 65 are pretty close. But you could also look at maybe this slope here from 0 to 1 and see that that looks a little steeper. Or from 0 all the way up to there, that's going to be different. Or how about from this point to this point, right? Do the change from 3 to 4. So they said this was 140, so we go 140 to 200. That's an increase of 60. That's going to be a slope of 60. So you can see all of these bits and pieces are going to have different slopes because the function itself has different slopes, right? It's increasing and decreasing at different rates. It's a curved function. It's not a straight function. So here's the general formula, right? The average rate of change of a function between any 2 points A and B is just f of b minus f of a all over b minus a. It's just a fancy way of saying slope of the straight line connecting those 2 points. Because if you look at f of b minus f of a, that's just a difference in your y values, right? That's a change in y. And b minus a, that's a change in x. So there's my change in y over change in x, there's slope, right? So it's average rate of change function is really just another version of slope. Here's some more examples. We can see that we can apply this to just about any function. And if we're going from 1 to 3, right, it's reducing. We all see that's a negative slope. And then if we go from 4 to 7, we can see it's increasing. That's a positive slope. So we already know our answer should be negative and positive. Now let's actually put some numbers in and see what we get. So for the first one, we got to do f of 3 minus f of 1. And if you remember, the function was x minus 3 squared. So f of 3 is just 3 minus 3 squared, which is, right, 0 squared. And then 1 minus 3, that's negative 2 squared. So we get 0 minus a negative 2 squared, but negative 2 squared is 4. But then we have this minus 4. So that's how we get 0 minus 4. And we just get negative 4. You go, yeah, that's right. We knew it was going to be negative. And then the other one from, the bottom part is we still have to do 3 minus 1. So negative 4 over 2. Negative 2 is our slope of our straight line between those 2 points, right? The net change is just the change in the y's, and then the average rate of change is the whole thing. All right, the other example from 7 to 4, again, we plug in 7 and 4 into the functions. Of course, we could have looked at the graph and figured out what these dots were, but then you're not totally accurate, right? When you're looking at graphs, you're like, oh boy, that looks like it might be a 1, but I'm not really sure. When you plug it into the function, you get actual precise answers, and you get a net change of 15, and then from 7 to 4, right? 7 minus 4 was 3, 15 divided by 3 is 5. So you can see we now have a positive change, right? So negative 2, positive 5, which makes sense. Negative 2, that's a negative slope. Positive 5, that's a positive slope. Okay, and like I mentioned before, linear functions have a constant rate of change, and that should kind of be a no-duh kind of thing, because a linear function has a constant slope of m, right? And as we've seen, the average rate of change function is really just a fancy way of describing slope. So obviously, any linear function you choose is going to have a constant rate of change. And here's how we can prove it to ourselves. We can check out what the average rate of change is of this linear function, right? Y equals 3x minus 5. And we just say f of x, same thing as y, right? And we're going to go from 0 to 1, from 3 to 7, and then we're going to go from 2 arbitrary points, from a to a plus h, some amount h. And look what happens. So when we go from 0 to 1, we get a slope of 3. When we go from 3 to 7, we also get a slope of 3. And even when we go from a to a plus h, right? So first you have to put in the second one, right? A plus h, and you go 3 times a plus h minus 5, and then minus 3 times a minus 5. You do the math, 3a, 3h, right? Blah, 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 all this stuff. The 3a's cancel. The 5's cancel. You're left with 3h over h. You divide, right? The h came obviously from the a plus h minus a. The a's cancel. The h is canceled and left with 3. So that tells us now for any a and any h, the slope is always going to be 3. And we go, well, no duh, because that function had a slope of 3, right? The function was y equals 3x minus 5. And so if it has a slope of 3, its average rate of change is always going to be 3. And we've kind of proven the point that linear functions all have a constant rate of change. And that's everything you need to know about average rate of change.